Hi everybody, let us continue the previous lecture and discuss the photon gas and the blackbody radiation. So it is a problem which was, the blackbody problem was solved by Planck in 1899 in, in the inception of quantum mechanics, the Planck postulate of a quantum of radiation, okay? But the blackbody problem is a very well-known problem in physics. It is relevant for the description of stars, the total power radiated by stars. Related to this problem, there is a law which is called the Stefan-Boltzmann, which was already known that the total radiated power by a black body, just like an incandescent lamp, if you want to consider a very uh, terrestrial problem, okay, an incandescent lamp produces a black body radiation, nearly a black body radiation, but the sun produces a black body radiation, the stars produce black body radiation, a highly heated metal produces something like black body radiation. Okay, so there is a history, a chronology to this problem you could find out, but here we want to calculate things using quantum mechanics and second quantization. But the Stefan Boltzmann law was related to the black body problem, which stated that the black body produces a total emitted power, a total radiated power or emitted power, which goes like the area of the object, the Stefan Boltzmann constant, times to the fourth power of the absolute temperature. Okay, this was an experimentally well-known law. Okay, it is used to calculate thermal equilibrium and to estimate temperature of the planets, and it's very interesting. There are very interesting applications for Stefan Boltzmann law. Also, you could calculate how uh, how much your body radiates. Okay, you have an average temperature of 36 Celsius. Okay, so you could convert it to the absolute temperature, and you could estimate the area of your body. And just to keep your temperature constant, you would have to produce an amount of power. Your body needs to consume energy coming from food, okay, just to keep your temperature constant, because you are constantly radiating to in trying to achieve thermal equilibrium with the medium. Okay, so it has a large number of applications for this problem, but also we can learn about methods and about the photon gas. And historically, this problem was discussed by Rayleigh Jeans, which is called the Rayleigh Jeans model. It is good only for low photon frequencies. It reproduces something called the spectral radiance, which is the radiated power as a function of the photon frequency. And it is a good model only for very low frequencies of the photon. It diverges. It leads to the so-called ultraviolet catastrophe, and it is a classical model. It is classical. model. Okay. Also, previous to Planck, there was the VN model. The VN model is a very good approximation for high frequencies, and it predicts quite correctly the shift of the radiation frequency peak as a function of temperature. The radiation peak moves to higher frequencies if the black body is at higher temperature. Okay, so for higher temperatures, the frequency at the peak of radiated power is higher. You increase temperature, the peak of the radiance moves or is at a higher frequency. Okay, so Planck knew all that, but he knew also that neither the Rayleigh-Jeans model or the VNs or the VN model correctly predicted the radiance over the entire spectrum. Okay, he put forward the idea of a quantum of energy, but here we will use the second quantized version for the photon gas, and we will calculate the averages and total energy and so on and so forth, and we will find out Stefan Boltzmann law for the black body, and we will see that this model is good at low frequencies and high frequencies, but Planck's law is a experimental success. Okay, so let me just discuss a little bit Rayleigh-Jeans ideas in brief. Okay, so Rayleigh-Jeans ideas. Rayleigh-Jeans already known that Rayleigh and Jeans already know that the electromagnetic radiated power from classical electromagnetism, okay, for classical electromagnetism, it has a power density which is measured by Poynting's vector, is proportional to omega squared. Okay, it's equal to omega squared times the modulus of the potential vector at that given frequency squared, and is divided by some constant here. It's proportional to. Okay, so each quadratic factor in classical statistics, the idea of Rayleigh-Jeans was that for each quadratic amplitude, so this is an amplitude at a given frequency and at a given k, so this frequency depends on k, for each you could replace by a factor of the order of kBT. Okay, so Rayleigh-Jeans proposed a law apart from some constant, which is an amplitude here, depending on some electromagnetic constants, perhaps speed of light, and it's just a constant. It produces something like this: kBT omega squared. Okay, so the intensity increases linearly with temperature and quadratically with frequency. So if you plot this for a given temperature as a function of frequency, you would find something like this: a quadratically divergent spectral radiance. So for omega tending to infinity, the radiance would diverge. Okay, it would diverge. They borrowed the idea of classical statistical physics, and they thought that for each degree of freedom, which is quadratic, you would have a factor of kBT. But this way, they found a divergent function. Okay, this diverges, and this divergence is is worse for higher frequencies for the ultraviolet spectrum, and this leads to the so-called ultraviolet catastrophe. It's because of this divergence. All right. So it correctly or almost correctly produces the values for very small frequencies, but it is incapable of predicting the high frequency behavior. So let us consider here the photon gas. Photon gas, Hamiltonian. It is very similar to the case of phonons, but we have the Hamiltonian in the following form. Now the operators correspond to photon, annihilation, and creation operators. This product here is just a number operator. You need to sum over all the values of K and all the possible polarizations. For notice, for photons, there are only two possibilities because the photon must satisfy this relation here. The polarization vector for a given alpha, it depends on K times the scalar product with K produces 0. Okay, and there are only two solutions for this equation, independent solution for this equation, because epsilon, which is the polarization vector, must be orthogonal to K. So we already know that photons are transverse wave solutions in the case of plane waves. Okay, so you don't have the longitudinal photon. Okay, in the case of phonons, you have longitudinal modes, but for photons, you don't have that. Also, you have that frequency of the photon is the speed of light times k. So this is the speed of light in replacement of the speed of sound. Okay, and this is the frequency, this is the wave number. This k modulus is equal to that factor. Consider linear dispersion, but for photons, you don't have a cutoff. The dBi frequency is a cutoff. For photons, you don't have that cutoff. Okay. Well, now the total number of photons in the problem corresponds to the same idea, summation over all the case and over all the photon numbers. Okay, and now we take averages. Average of this corresponds to the average of the number. Average of this, average of this. Okay? But this average is just Bose-Einstein distributions, which we already discussed in previous lectures concerning Bose-Einstein and Fermi-Dirac statistics. Okay, so again, we can replace summation over k and alpha by integrals. volume divided by 2 pi to the cube in 3 dimensions, of course. But now we have two possible polarizations, so a factor of 2, and the integral is an integral over d3k. All right, this is an integral over d3k. And this way, you would have the average of the Hamiltonian, the total internal energy of the photon gas, and the number of photons. They will be equal to volume, 2 times volume. And if we integrate over all the energy, you would have a 4 pi, because the integral over d3k is just a 4 pi integral k squared dk, which produces something like 4 pi to the speed of light to the cube, an integral of omega squared d omega. Okay, so this is it for this factor here. You could insert 4 pi. This produces an 8, which cancel this here. So you would have a volume divided by pi squared c cubed, this h bar here, and an integral running from 0 to infinity, omega cubed, omega times omega squared, d omega, divided by e to the beta h bar omega minus 1. Okay, and the total number of photons will become volume divided by pi squared divided by the speed of light cubed, an integral from 0 to infinity. Okay, um, and this produces just a factor of omega squared d omega e to the beta h bar omega minus 1. But now we can already apply the idea of replacement. X is equal to beta h bar omega. If we replace that, what we will find out for the photon gas is the following. It is the following. The internal energy of the photon gas will be given by the volume, and I can divide it by the volume. So this is the internal energy density of the photon gas. Let me call it the internal electromagnetic energy density. It is equal to h bar divided by pi squared c to the cube. And if we replace each omega by this factor here, we will have a kBt 4th power t to the 4th power. Okay, and h bar will be 4th power in the denominator, so we could write it as the 3rd power here, because cancel one of the factors here. And the integral, the resulting integral, will be of the form which we already encountered in the case of photons. So you would have a pi squared divided by 15, and this is a constant times the 4th power of temperature. Okay, this is the 4th power of temperature. Specific heat of the photon gas will be proportional to pi squared Boltzmann constant to the 4th power divided by 5 here, or 4 divided by 15, sorry, t to the cube. All right, so these are the laws, the general laws for the photon gas. Of course, you could calculate the total number of photons in the gas, but the total number of photons will be proportional. Let me write it as equal to some constant, and from 3 factors of omega squared times d omega, replacing by x, you would find some constant here. Let me use a factor b times t to the cube. This is photon number in the photon gas. Okay, so for the pressure of the photon gas, pressure, the pressure, it is proportional to the internal energy, the electromagnetic internal energy. There is a constant of proportionality, but this goes like this is equal to some constant. Let me call it A times T to the fourth power. So for the photon gas, pressure goes to zero if temperature goes to zero. And also, I didn't say that previously, but also for the phonon gas. Okay, so the pressure coming from bosonic degrees of freedom, as temperature goes to zero, the pressure vanishes, which means uh, in sharp contrast to the fermionic degrees of freedom, which produces a pressure which is the so-called the degeneracy pressure. Even at zero temperature for fermions, there is a pressure of the gas, okay, internal pressure, which prevents from collapsing. For bosons, such pressure doesn't exist. So at zero, at the absolute zero, the pressure is zero. Okay? But it is a very important aspect in the dynamics of stars. Okay? For stars, you have a pressure, an internal pressure, which comes from the degeneracy pressure of the fermions, and also there is a pressure from coming from the photon gas, which helps to stabilize against the gravitational collapse. Okay, so this pressure factor here for the photon gas plays a relevant role in the structure of stars, the structures of uh, very massive bodies like stars and galaxies and so on. It helps. It is not the only contribution, because you have the pressure coming from fermionic gas, but also this pressure helps to stabilize the structure. Okay, so this is a radiation pressure, and it is proportional to the energy density, and therefore it's proportional to the fourth power of the temperature. Also, the radiated power of the photon gas, radiated power, it is proportional. It is proportional, the total radiated power, it is proportional to the internal electromagnetic density, energy density. So you would have a fourth power dependence of the radiated power, the total radiated power. But this is an experimental fact. This is the Stefan Boltzmann law. So the proportionality here for the total radiated power will be the Stefan Boltzmann constant times the area of the object. But it's proportional to the radiated power, is somehow proportional to the electromagnetic density. And this goes like the fourth power of the temperature. Okay, so here you have something which resembles the Stefan Boltzmann law for radiation, for the emitted power of a black body, of a black body. Well, the Planck, let me discuss a little bit about the power emitted by a black body. Let us borrow some ideas from the electromagnetic theory. You could you could write it in second quantized form, the average of the Poynting vector over a period in time, and you could calculate also for a given temperature. Do not be confused. This is absolute temperature, not the period. I am writing the period. The time period is 2 pi over omega for a given omega. And this is the average of E times H, which is the electric field times magnetic field. This is the power density, okay, the radiated power. This is Poynting, the average of Poynting's vector. But I will discuss Poynting vector considering quantum mechanics, all right? So suppose you have a surface here, a surface whose unit vector points in the direction of the area. So this is an infinitesimal, a delta of area, okay? This is a delta of area, okay? And here we would have a photon propagating in the direction of n, depending on the k vector, okay, for that photon, sorry. And here we could consider a small volume near that surface. Near that surface, they form an angle of theta here. Okay, they form an angle of theta, and there are a number of photons here propagating. Okay, there is a photon density here. So there is a photon density inside this small cube or a small volume with surface area traversed by these photons delta A, and this is a delta L, which I will consider to be given. This is a side of this volume, which I will consider to be connected to the speed of light by this formula. The speed of light times delta t. Okay, so just consider the following. Poynting's vector is the energy traversing area delta A divided by the area divided by delta t in some direction of space. So in some specific direction, the maximization of this vector corresponds to the area oriented in the direction of the photons traversing this area. But now take into consideration that the total energy traversing that area corresponds to the summation over all the wave vectors and all the alphas. Okay, I will consider the modulus of that. Okay, I will consider the modulus of that. And this corresponds to the total number of photons, h bar with energy h bar omega k, which cross that area. So only photons whose wave vector k is in the direction, the component of the wave vector is in the direction of the unit vector representing the area. So the unit vector is perpendicular to the surface. So here we will have the following. We will have photons propagating in the direction n of k, dot product, because I only want the projection, n of the area. Okay? And this is divided by delta of area, because it's the energy divided by the area, divided by delta t. And delta t, if you consider this total number of photons in this volume here, this volume to entirely cross that area will take a delta t which corresponds to the delta L divided by C. Okay, so delta t I can write delta L over C, so over the speed of light. So inserting it here, you'll have a factor of speed of light, which is a constant. I can multiply by h bar divided by delta L. But this is just the volume. This is just the volume. So here I am considering the projection of the pointing vector in the direction of a specific area here. Right? So this is it. And we will have this in the following way. We will have 1 over the volume, a summation over all the k's, all the alphas, the polarizations, h bar c omega of k times the cosine here, because just for directors or versors, you have the cosine. So remember, a scalar product of two vectors produces the modulus of the first times the modulus of the second times the cosine between the two. Okay, this is it. So we need to sum over all the values of k, right? And the black body is composed of many infinitesimal surfaces. But I am calculating the flux, which is going outside this volume, this region here. Okay? So this cosine here comes from the so-called Lambert's law. It is another way to say this factor here comes from where this factor comes. This comes from an empirical fact, which is so-called the Lambert law. All right, and we will have this as the total power density. Okay, so this is the power density crossing this area, because I can now integrate over all the entire area of the problem and divide by calculate the total power crossing the area of the black body and divide by the total area. But this is a local measurement here. This is local. Okay. So this is the average S. Okay, the average S corresponds, it is the emitted power per unit area. Okay, so this is watts per square meter. So if I multiply by the entire area of the black body, I will have the radiated power, the total radiated power, or emitted power. A black body is understood as a body which is in thermal equilibrium, so it emits and absorbs at the same time. Okay, so the emission for a given area here, you have a photon. This is the area. You have a photon here. Photons which are emitted to the outside of the body corresponds to the theta angle running from 0, which corresponds to parallel vectors, to 90 degrees, because if you go from 90 degrees to pi, it corresponds to absorbed power, perhaps. And this way, we will have 1 over the volume, a summation over k and alpha, which is polarization of the photons, h bar times the speed of light times omega, depending on k, times the cosine of theta. Okay, this is the total radiated power. Now we can convert again a summation over all the k's, all the alphas into the following: twice the volume, because there are 2 photon polarizations for each k, divided by 2 pi to the cube, and integral over d3k, right? Over d3k. So the total radiated power corresponds to volume cancel out. Notice area of the body, the area of the body, the black body, the total area of the body. It is a factor times a factor of 2 divided by 2 pi cube. Okay, and when we convert this into integration, we will have an h bar factor, which we can put outside the integration symbol because it's constant, times omega coming from here, a k squared dk coming from this here. Now we cannot replace the integrals of the angular variables by 4 pi because there is a cosine function here, and this cosine function needs to be integrated with respect to theta, as we said, from 0 to 90 degrees to pi over 2, and the integral over d phi, this corresponds to a factor of 2 pi, right? So, and I'm sorry, I was forgetting the average number of photons traversing the area. So we need to introduce the average value of photons. We already know what is that. That is just Planck's law, or Bose-Einstein distribution. Okay, this comes from Lambert, this factor of 2 pi. It is because no matter the phi angle, which is measured in the area local plane here, so it's an azimuthal angle, it doesn't matter, it produces a factor of 2 pi, and we will have the following: the total radiated power will become twice h bar c divided by the area of the black body. Okay, I will divide by the area. This is just S, is just 2 times h bar c. A factor of 2 pi cancel one of these factors here, so we have a 2 pi squared, pi squared. If we replace from 0 to infinity, of course, if we replace K by omega over C, we will have a factor of C cubed. It cancels one of the factors of C. So we have C squared and integral omega to the cube divided by the omega divided by e to the beta h bar omega minus 1 from 0 to infinity. Right? And of course, you have to deal with this cosine of theta, sine of theta, d theta. Right? This is the same as replacing this by u, this as a du, and you can switch the limits just to eliminate a sign here because this is minus du, okay, and this corresponds to the same as an integral of u du from 0 to 1, okay, from 0 to 1. But now you can calculate the integrals. Of course, you'll have 2 times h bar divided by a factor of 2 pi squared c squared. If you integrate it, from 0 to 1, because cosine is a at 0 is a 1 here, and pi over 2 is a 0, so you switch the limits of integration. You have u du. This is u squared over 2. It's because uh, evaluated in the limits. You have a factor of 1/2. This 1/2 cancels this one. You'll have an h bar there, of course. And if you again replace x by beta h bar omega, you already know you'll have a pi over 4, pi to the 4 divided by 15 Boltzmann constant to the 4th power, temperature to the 4th power if you integrate this equation here. And this is just Stefan Boltzmann constant times 4th power of the temperature. Notice that Stefan Boltzmann constant just depends on the h bar. Here you'll have a factor of 4 times that, so it's factor of the cube. Here you'll have pi to the 4th, Boltzmann constant to the 4th. So you could eliminate a factor here squared divided by 16 here, 60, sorry, c squared h bar to the cube. This is the Stefan Boltzmann constant. If I didn't miss any factor, okay, just be careful in the calculations, but you can reproduce that. If I didn't miss anything, this is Stefan Boltzmann constant. So this Stefan Boltzmann constant. Okay, but there are other interesting aspects here. Planck's spectral radiance. This depends on omega. There are many ways to represent that. You could represent it as a function of the frequency in hertz. This is in radians per second. You could also represent it in terms of the lambda, in terms of the wavelength. But I'm just using this factor here. So it corresponds to 2 times h bar divided by 2 pi squared c squared omega squared omega to the cube, sorry, omega to the cube divided by a exponential, the Euler number, to the beta h bar omega minus 1. This is Planck's radiance formula. Okay, depends on frequency, depends on the temperature via the factor beta. Okay, another constant can be plugged in here. You could just define other constants, but notice this is just the integrand here times this factor, this common factor here, and that integral from Lambert's law is not considered at a first moment. Okay, you need to integrate that to obtain Stefan Boltzmann's law. Okay, so uh, this formula here, notice the following. If you plot that against temperature, oh, sorry, against frequency I of omega for many betas, for many temperatures, you'll find out the following. For a given temperature, you have this. For a higher temperature, you have this. Okay. So this is temperature T1. This is temperature, another temperature higher than the first. Notice there is a displacement of the peak, omega 1, omega 2. The amplitude increases. Okay, amplitude increases. And you could calculate where is the maximum of this radiance formula, so you could find out the derivative of the intensity with respect to frequency equal to 0 to find out peak. Okay, and this I will let you calculate that as an exercise. So this is Wien's displacement law. You need to find out that law just calculating this derivative, of course, but it also predicts for two limits. Two limits. Okay, you have beta h bar omega. Okay, in this exponential here, you could make it much smaller than the unity, and therefore you will have Rayleigh jeans. And you have another limit where Wien's law applies. Okay, so if this exponential dominates, because beta h bar omega is a very high number, it is valid for high frequencies, because for a given temperature you could increase the omega. Remember, beta is just the reciprocal of the temperature here. So this exponential dominates over the unity, and Wien's law would be of the form omega cubed e to the minus h bar omega over kBt. Wien didn't know what was this constant here, but he already have had knowledge of the behavior. So here for high frequencies, you have an exponential decay, so a Wien law. And here in this other side, Planck's correctly predicted the omega squared behavior. Because in this case, in the Rayleigh-Jeans regime, this factor here can be expanded. E to the beta h bar omega is approximately 1 plus beta h bar omega. And therefore, Planck's constant, which is a quantum mechanical number, is intrinsically quantum mechanical, disappears, and you'll have a radiance which is proportional to omega squared, because you cancel one of the omegas, the h bar is cancelled, divided by c squared, divided by speed of light squared, times kBt, because you will have a beta factor here in the denominator, and this produces the factor, the inverse of beta produces the temperature factor here. So this correctly predicts the Rayleigh-Jeans behavior at very small frequencies. It predicts the Vn law at very high frequencies, but it is successful over the entire range of frequencies. Okay, if correct, the Big Bang theory predicts a thermal radiation, which is the so-called cosmic background. It is a blackbody radiation. It has been measured, and some scientists say it is a confirmation for the Big Bang theory, and it is so-called the most perfect blackbody radiation spectrum being measured. But the temperature at, at the peak here, the peak for the Big Bang or the cosmic background radiation corresponds to a few kelvins. Okay, this frequency, the peak frequency corresponds to a few kelvins, and it is a frequency in the microwave domain. Okay, but of course, an incandescent lamp will have a behavior like this. When it's heated, you would have a hundreds or thousands of kelvins. It will produce a form of blackbody radiation. Okay, and with this, we finish the discussion of Bose gases. Okay, bye bye.